Hey friends, Vincent here, welcome to Fearless in Rust, where we make Rust clean and simple. Let's get into it. Today, we are looking at another classic structure used to build block ciphers, Substitution Permutation Networks, usually called SPNs. Unlike face-tone networks, SPNs rely on layering several simple operations across multiple runs to build a secure cipher. You'll find this structure in many modern designs. For example, AES, the most widely used symmetric cipher today, is built as a substitution permutation network. Other ciphers like Camellia also use this design. But before we go further, one important warning. Software implementations of S-boxes can sometimes leak secrets through cache timing attacks. That's why modern AES implementations often use hardware instructions like AES-NI or carefully written constant time libraries. For learning post-post-4, implementing an SPN in Rust is a great way to understand how modern ciphers are structured. So, in this video, we'll write a tiny SPN round in Rust, encrypt a small block, then reverse the process to decrypt it. Let's start with the core idea. A SPN round is usually built from three operations. First, substitution. Second, permutation. Third, key mixing. Let's break those down. Substitution means replacing each byte with another value using something called an S-box. An S-box or substitution box is simply a lookup table that maps one value to another. Like, let's say, that one, for instance. The goal is to introduce non-linearity. That means the output doesn't follow any simple mathematical rule based on the input. Without non-linearity, attackers could model the cipher using linear equations and break it much more easily. Permutation comes next. Permutation simply reorders bits or bytes. Its role is to spread the influence of each input bit across the entire block. Finally, we mix in a round key, usually using XOR. This step injects secret key material into the data. Together, substitution and permutation give us two essential cryptographic properties described by Claude Shannon: confusion and diffusion. Confusion hides the relationship between the key and the ciphertext, and diffusion spreads the influence of each input bit across many output bits. Now, let's implement a tiny SPN example in Rust. We'll encrypt a 4-byte block using a simplified S-box and a simple permutation. Let's jump into Rust. So first, we define a small Xbox table. Normally, an Xbox contains 256 values, but for demonstration, we will use a shortened version. So here we manually define, I can take the same example. We manually define a shuffled S-box, shortened for the demo. This table maps each possible input value to another value. Next, we define the block we want to encrypt. So let's declare input variable. So here we will have 4 values of U8 type, and let me just copy paste the 4 values. Right here. Now comes the substitution step. Let's put some comment. Substitution. Okay, we replace each byte using the S-box. So let's declare this variable. So here's the same. Take 4 values of type U8. And here, so let's use the input variable, and let's use a map function. So here, as a closure, let's use just B. And let's use the S box right here. B as U size. Notice that the input and output must have the same size. If we tried to access an index that doesn't exist in the S box, the program will panic at runtime. Now comes the permutation step. Here we simply reorder the bytes. So let's do that. So first, let's move the byte 2 to position 0. Oops. Then the byte 0 to position 1. Then the byte 3 to position 2. And finally, take the byte 1 to position 3. Take, just close, okay. This spreads the influence of each byte across the block. Finally, we mix in a round key using XOR. Take, let's say this will be the XOR step. Okay, so first let's create the round key. Take okay, just this way, and let me just copy paste the value for the round key. Now let's declare an encrypt variable. An encrypted stores the final result of the round after mixing the data with the round key using XOR. So let's use permute. Okay, first I need to iterate over the permuted bytes. So let's use the iter function. Then we need to pair each byte of the data with the corresponding byte of the round key. For that, let's use the zip function with a round key and iterate over. Then, for each pair, I apply XOR. This mixes the data with a key, which is a basic step in many block ciphers. Let's use map for that. As a closure of the two terms, A and B. And let's XOR them. Okay, then we need to collect the results into a vector. So collect function. Right here is gonna be a vector of U8. Okay. Then I convert the vector into a fixed array with try into. And because I know the size is exactly 4 bytes, I can unwrap. Yeah, it's a comma right here, not dot. Okay. Now, let's print each step so we can see what happens to the data. So let me just pass case of println, take it's gonna put right here. Take start server. Yeah, that's okay. Sometimes I just need to restart the Rust analyzer. Oh yeah, sorry. At that point is not an equals. It's double dot. Then right type. Take. Okay. Okay, we are done. So now take cd rest. Okay, and we can go example. So in my case, it's 0. Take coding SPN. And just like in my previous video about the 5-star example, the exact numbers are not what matters. What matters is how each transformation changes the data. Like you can see here. We have the input, substituted port, permuted step, and encrypted data. Okay, now let's show the interesting part, how to decrypt the block. For SPNs, decryption simply runs the steps in reverse order. So instead of substitution, permutation, and XOR, we do XOR reversal, permutation reversal, and inverse substitution. So let's implement that. And let's put some command. So decryption ports. And right here, encryption ports. Okay, first we recreate the same as box. Let's say inverse. Inverse S box. So here just 0 value of UA type and 256. So the inverse S-box has 256 entries because X-box outputs are bytes. Since a byte can be 0 until 255, we need a table large enough to index any possible values. And now let's build the inverse S-box. So here, I'm gonna iterate over the S-box with enumerate to get both the index and the value. Then I built the inverse S-box by storing the reverse mapping. The S-box output becomes the index and the original position becomes the value. So let's do that. So here we need the index and the value coming from the S-box. Let's enumerate onto. And here let's build the inverse in Xbox. Take val as usize equals 8 as u8. Okay. This table lets us reverse the substitution. Now we start from the encrypted block. So, as we have seen here, let's create the encrypted block variable. First, we undo the XOR with a round key. So let's say let XOR reversed. So here the same, you wait for, and let's use the encrypted block. And here the same. Let's use a header function, then the zip has the same way, using the round iteration over the round key. Then mapping, with two terms, and net doing the XOR. And let's collect the result. Take vector of u8. Just check. Yeah, I know. I didn't propose to me a correct because I forgot parenthesis at that position. Okay, now let's use a try into, like during the encryption part, and let's finish with an unwrap. Okay, next, we reverse the permutation. Remember, our original permutation was 2031 at that point, 2031. So the reverse permutation becomes 1302. So let's create permuted and reversed. Okay. Here the same, you 8 4 equals take. So let's use the XOR reversed. So first one take up 1 3 0 2. Finally, we apply the inverse Xbox. So let's create a decrypted variable. Wait for equals so permuted reversed, and let's use a map function here. As closure, let's have one term. And let's use the inverse as box. Take p as u size. Okay. And let's print these steps again. Now let's run the program. Just like before, the decrypted block should match the original input. That's how a SPN cipher can be reversed. As you can see, encrypted step, XOR reversal, permutation reversal, and for the input right here and the decrypted, we have the same value. Now, let's close the loop with a summary. Substitution permutation networks build secure ciphers by repeating 3 simple steps. Substitution introduces confusion, hiding relationships between input and output. Permutation introduces diffusion, spreading the influence of each byte across the block. K-mixing injects the secret key into the data. These two ideas, confusion and diffusion, were introduced by Claude Shannon in 1949, and they remain the foundation of modern symmetric cryptography. By repeating these operations across multiple runs, SPNs create the structure behind many modern block ciphers. In this video, you have seen how that mechanism plays out in real Rust code. Thanks for your time, see you later.